Okay, so now let's move forward towards another algorithm, that is random forest. So let's start with the decision tree first. Decision tree are very awesome. We have already seen about, we got a very intuitive idea about it. Now they fit almost every pattern in your data set, but that's a catch. They are very fragile, like really fragile. You can change a few data points in your training set and you might get completely different tree. Okay, that we called as a very high variance. Now in machine learning we have the concept for the bias variance trade-off, which we have already seen, that every model error has two components: bias, which is underfitting, and variance, which is overfitting. So a deep decision tree has almost zero bias. It memorizes everything, but variance is at its roof. Okay, so to solve this problem, we got over with the averaging part. Now here the institution is, if I ask one person a question, they might be wrong, but if I ask 100 different people and majority votes, I'll probably get a much better output. Okay, so that's the core idea behind the random forest. Mathematically, if you have b independent predictor and each with variance sigma square, their average has variance sigma square divided by b. So the more tree you add, the lower your variance gets. But here's the problem: if all your trees are trained on the same data, they are going to be heavily correlated. They'll all make a similar mistake, and correlated tree doesn't reduce variance as much. The formula for the variance of an ensemble is rho times sigma squared plus a term that goes zero as you add more trees. That row, that correlation is what limits you. Okay, so random forest solve the problem in two ways. First, bootstrap sampling. Second is the feature randomness, and both of them together makes random forest more powerful. Moving forward towards section 2, that how it actually works. Bootstrap sampling: for each tree, instead of training on your full data set, you train a random sample with replacement of the same size. If you have 1000 data points, you sample 1000 points, but with replacement, meaning some points appear multiple times and some doesn't appear at all. On averaging, each bootstrap sample contain about 63% unique data points. The remaining 37%, they are called as out of bag samples, and they become super important later. Okay, so you do this b times, let's say 500 times, and you train one full decision tree on each bootstrap sample. That gives you 500 different trees, each slightly different because they were trained on slightly different data. Now second step is the feature randomness. Now you have the exact twist that separates random forest from a plain bagging. At each single split in every single tree, instead of considering all features, you only consider a random subset of m features. For classification, the default is square root of p, where p is the total number of features. For regression, it's p divided by 3. Now, why does this matter? Because in regular bagging, if there is one strong feature, every tree will use it as a root. Okay, all trees look similar to it, so they are correlated. Feature randomness focuses more on to explore different features, making them more diverse, more decorrelated, and directly reduced out row from the earlier formula. Step 3 is the aggregation. Okay, once all the trees are built, prediction is simple. For classification, majority vote. Each tree votes for a class, and whichever class gets the most vote wins. For regression, you just have to average all the tree prediction, as simple as that. Okay, so now let's talk about the 37% out of bag data, because this is the one of my favorite thing about the random forest. Okay, every tree was trained on roughly 63% of the data, and the other 37% is the OOB samples, out of bag samples, which were never seen again by which were never seen before by the tree. So you can use this sample as to test the tree. For each data points, you collect all the trees that didn't train on it and make a prediction using only those trees, so, and compare it to the true level. This gives you the OOB score, a nearly free cross validation estimation with zero extra computation. Just set the OOB score to true in scikit-learn and you'll done. Okay, one more thing is the feature importance. Random forest gives you two ways to measure this. First one is the MDI, mean decrease in the impurity. For every split in every tree, you record how much the split reduces the Guinea impurity weighted by the number of sample. Average this across all the trees for each feature. It's fast, it compute during training, but it can be biased towards features with more categories. Second one is the permutational important, also called as the MDA. After training, you take your OOB data, shuffle once features value completely at random, and then measure how much the accuracy drop. The big drop means that the features were important, and slower means that the features are not so important. This process is completely slow but much more reliable. Okay. Moving forward towards the hyperparameter and comparison and the key takeaway, we have hyperparameter to go forward with it. N estimator, this is the number of trees. More trees is almost always better, but within the dimensional returns. Start with 100. If your OOB error is still improving, go high up to 500 or 1000. Now, here are some of the important points that adding more trees can cause and can never cause overfitting. More trees only smooth out the prediction. Okay, second is the max feature. It is most important impact hyperparameter. It control how many features are considered at each split. Smaller value means more decorrelated trees, but weaker individual trees. Third one is the max depth. By default, trees grow fully, so you can limit the depth to reduce the memory usage. Third one is the min sample split and min sample leaf. These control when a node can split. Higher value means simple trees, slightly more bias and less variance. N jobs equals to -1. This tells scikit-learn to use all your CPU core in parallel. Since trees are built independently, you need nearly linear speed up for that. Third one is the OOB score equals to true. Always enable this. Okay. Fourth one is the now random forest. Now we have some discussion about the comparison random forest versus the decision tree. A single decision tree is interpretable, fast to train, but has a high variance and can overfit easily. Random forest has low variance and is resistant to overfitting, gives you a stable feature importance. The trade-off, it's slow to train, B times slower, but it's basically a black box. You can't visualize a forest of 500 trees the way you can visualize a single tree. Finally, the limitations for the random forest are that it reduces the variance, but if you have a single decision tree that is already in underfitting, it has a high bias, and random forest won't be able to fix it. So more trees reduces the bias, and in that case we are moving forward towards the gradient descent, which we'll be talking about in the upcoming lectures. Algorithms like the XGBoost, Light GBM and all. Also one more important thing, that MDI are importantly so that can be biased when the features are correlated or have many categories. Use permutation importance in those cases. Okay. Moving forward to wrap up completely, we can wrap up in 5 key takeaway points. That random forest equals bagging plus feature randomness. You need both ingredient. Second, more trees never overfit. They only reduces the variance until it converge. Third one is the OOB score is free cross validation. Always enable it. Fourth one is the MDI is fast but biased, so use permutation importance for reliable feature ranking. Fifth one is random forest reduces the variance, not bias. If a single tree underfits, switch to the gradient boosting. Yeah, thank you.